Um, okay. So before we start our lecture, I wanted to talk about our final project so that we could, everyone can start thinking about it. So the final project for this class is going to be basically an application of what we've learned in practice. So it's one thing to kind of learn the concept through class and practice in homeworks, but I think that what we really want out of this is be able to apply it to your research and for it to be as useful as possible. So in terms of maybe keeping everyone on track for this thing, we'll have a set of deliverables. So I'll be having a project proposal due about a third of the way through May. And the proposal will mainly be so that it's kind of in previous years, without the proposal, people have kind of waited till the last minute to put a lot of this together. And so this will be at least one way to keep you guys thinking about the work and the data a little bit ahead of time. I had originally scheduled the project presentations on the last, in essentially finals week. And the report has to be due at the end of finals week so that I have enough time to grade them. And originally, the presentations were pushed back to finals week instead of the week before, because I actually had originally had a conference, but since that's not happening anymore, I don't know, what do you guys think? Would you guys rather have more time to do the presentations, but then have less of a time to incorporate feedback before the final project report? Or would you guys rather bring the presentations back up 1 week, sort of how I usually organize it, so that you'll have like one less week to do the presentations, but you'll have an extra week to incorporate feedback into your report. I guess if there are any opinions about that, you can let me know. Ooh. Okay, so it sounds like everyone's kind of in agreement here, or at least 4 people are. So I'll sort of take that as representative. So we'll actually move up the due date, and I'll make sure to post this on Canvas. Okay. So in terms of the project proposal, it's pretty straightforward. It's like you don't need to worry about like the grading or anything, or looking for something specific. Basically, I want to be able to get a sense of, is the data set interesting, and more importantly, either what you're proposing is kind of within scope of the class. It's not too simple, or it's not too complicated, which can often be the case. And so getting a sense of how big the data set is, what's inside of it, and then talking a little bit about what you're interested in examining. And again, it's flexible. It probably is going to change anyways. but this will be a good way of getting initial feedback from me to determine whether or not the project is kind of well scoped for this class. For the project presentation, it'll be a 15-minute presentation. What have you learned from the data? Interesting tidbits and overview of the data. And then looking at your data analysis results or preliminary results, right? Because you'll probably have some feedback to incorporate for the report. Project report, it can be a short report. You don't need to like worry about the length or anything, just mainly focus on the content. I'm definitely pretty interested in you know, the analysis itself, but also I always think that it's a nice summary to understand the data pretty well. So what sort of issues you ran into in terms of data cleaning, and then you're encouraged to do data like preliminary like summary analysis, even producing, you know, graphs before you do any regressions. And that's always a good way of identifying like key variables, being able to identify patterns of interest and correlations and that sort of thing. And so, you know, there's a lot that goes into reviewing the data that can actually help to inform how you approach the data analysis. So incorporating that information into the report will be crucial as well. And then obviously we'll want to include analysis that you learned in the course, but you don't have to kind of do this checkbox and go through everything. It should just be stuff that's, if it's relevant for what you're doing and we learned it in class, then include it, but don't just do it because it's something that we covered in class. And of course, you know, that'll come with, I can provide feedback about what things sort of make sense to do and what things probably can be left out of the analysis. Okay, I see a question. What is meant by data overview? Yeah, so that's kind of like the more basic stuff about looking and summarizing your data. I mean, in a sense, it's kind of data analysis, but not in terms of what we've been doing in the class. So, you know, making scatter plots or bar plots or histograms, and being able to look at what essentially visualizing your data, right? And so that's kind of like a prior step to a lot of the, you know, regression analysis that you're doing, where you're trying to understand relationships between variables. And so data overview is basically like, you know, if you had a big data set and you wanted to understand it a little bit, you know, even before you do analysis, these are the sorts of things that you would want to do. Great. Okay. So let us continue on. To today's lecture. Oh, actually, there was one other thing that I just wanted to quickly mention. I actually recently stumbled across this thing. I don't know if anyone else has heard of it, and probably less useful, unfortunately, for the folks who are committed to Python. But there is this thing called Tidy Tuesday. And it's a weekly sort of quote unquote contest. Um, it's not really a contest, but basically every week this group um, they provide a data set, um, a sort of curated data set, and the whole idea is a bunch of people will create visualizations, and it's mainly for ggplot, and it's got a lot of it's got a big range everywhere from people who are just beginning to learn how to do visualizations all the way to pretty advanced folks, like way more knowledgeable than I am, and it's one of the neat things is that everyone sort of looks at the same set of data and creates visualizations and plots and graphs and that sort of thing. And after you sort of struggle through the code and making the graphs yourself, you can actually look at what other people made and the code corresponding to that. So yeah, it's been pointed out to me as a pretty nice resource for like a hands-on way of learning ggplot specifically, but even more generally, how to approach visualizing data. So I just wanted to turn you guys onto that. If anyone's interested, you can just Google Tidy Tuesday and look into that. I'll probably start to try it out starting this week. Okay, so that's called Tidy Tuesday. Okay, so to start off today's class, I want to formalize this concept. Okay, hang on. Yeah, so I got a message after the homeworks are submitted. Can we share coding approaches to problems to see how others did it? Yeah, absolutely. I think that's a great idea. If folks want to do that, I'm yeah, more than happy to help facilitate the learning process. If you want to share homeworks after you turn it in, that's totally fine. Let's see. Oh, I should also make an announcement about the homeworks. Sorry, before I forget. So I'm actually delaying homework 2 turn in by 1 day, or extending it so that everyone has 1 extra day, because in case you didn't see the announcement on Canvas, I slightly messed up the functions in problem 1. And so please take a look at the Canvas announcement to see what the changes were. And hopefully it'll make the interpretation of the functions a little bit more sensical, because there were apparently a couple edge cases that were going to mess up what I wanted the functions to do. And those have been fixed, so go ahead and take a look again. Okay. Starting with the lecture, finally. So I have been talking about I'd been talking about throughout the class this concept of overfitting. So we're going to formalize this a little bit more. So we've got our x's and we got our y's. And essentially, we've got some set of points like this. And we have a line that may go through the points And we've been discussing this concept, how we can create a better fit by adding more variables or by changing the functional form. And so as I add more variables, it's kind of hard to see here. I'll just call that sort of x1. Your line may end up looking, as we were saying, something like this, right? And so if you have if you modify the functional form or you add enough variables, you could get a perfectly fitting data set. But the issue that we're concerned with is that in an out of sample data, so if we start to throw in data that that your model fit is not actually calibrated on, you may do a worse job with the overfit model because it's too specific to calibrating on the data that you've included. So generate more points via f of x equals y, and suddenly model is bad, right? So hopefully everyone can sort of visually understand what's going on here. And so there's this question of at what point do we sort of balance this trade-off between adding more and overfitting it too much? And so we've talked about this idea of essentially minimizing the out of sample mean squared error, right? So one of the ways we do that is through cross-validation, in which we learn this k-fold technique, which is one of the methods with which we would attempt to find the balance. But to talk a little bit more conceptually about that, the sort of proper theoretical discussion of this is known as the bias-variance tradeoff. Oops, not variation, variance. So some of you guys may have seen this sort of graph before in talking about accuracy versus precision. It's kind of a similar concept. So low variance, high variance, low bias, high bias. So if you have low bias and low variance, so if you imagine this is kind of like a dartboard, it may look something like this, where you have a lot of your stuff being really quite accurate. And then if you have high variance but low bias, you are kind of centered in the right area, but your points are more spread out. When you have high bias, but low variance, you have a sort of dense set of points, but they are not centered in the right area. And then if you have high bias and high variance, you're going to have a big spread of points sort of in the wrong area. And so this is the basic concept of bias, which is your expected value is basically in the wrong place, whereas with high variance, the spread of data is pretty wide. So this can actually be formalized in mathematical terms. And so I'll write that sort of, this again is one of these things for reference, but you don't need to memorize this or anything. So the error is the expected value of your y minus the fit. And that is equal to something like this. So when we talk about the components of your error term, it is composed of these three things. Hang on, let me make sure I have all of my parentheses. Yes. Okay. So you've got this term, you've got this term, and you have this guy over here. And so the components of the error in your model are equal to your bias squared plus variance plus your noise. So when you have, oops, one sec. When you have overfitting, then your variance is too high. And when you have underfitting, the bias is too high. So okay, I see. Oh, I see. There's a comment. I think that there's an extra bracket happening. Yeah, so this, yeah, there was a little extra bracket in the variance term. Let me double check to make sure this is right. Okay, yes, there should be a bracket. Okay, hang on. It should look like this because it's the entire term squared. Okay. So there's a question, is bias defined for the error or data points? So the bias is the error. It's a component of the error of your model. So it is the way in which your model fits the data. And bias is essentially saying your model is like systematically incorrectly is systematically incorrectly predicting the data. So in other words, there's a difference between something like a model that has here the fit would have pretty high variance because the points are spread out from the data, right? And maybe I could improve that variance by improving the model in some way that gets closer to the data points. So that would be an example of high variance. For high bias, your model is, regardless of how the variance of the data is in the fit, it's systematically sort of wrong. So I could have like a really tight cluster of points here. Okay. And then maybe my line goes something like this. And in fact, one of the worries that you have is that having a model, when I predict these in when I predict the points in model 2 compared to model 1, I may actually get closer because the points themselves just happen to be kind of closer to my fit. But on average, 1 is kind of correct. But number 2 is not. It is systematically under predicting what the points are. And so there's, as you modify the fit of your model, and you modify your model in general to reduce bias, you inevitably actually increase your variance. And so that's one of the sort of fundamental trade-offs between this concept of overfitting and underfitting, is specifically a trade-off between bias and variance. So one of the charts that I think is really sort of quintessential here is when we talk about developing your model. So model complexity, and there are lots of ways that your model can be complex, right? So we've talked about adding more variables, and as you add more variables, your model gets more complex. And for example, your R-squared will always increase with more data that you put into the model because you're better able to capture some of the variation. But there are other ways to do model complexity as well, or to make your model more complex. So changing the functional form, which we'll talk about later, and actually even today we'll look at some machine learning tools that will help to improve the model. And there are certain factors that lead to higher model complexity. Yes. So okay. There's a question here. Did I say that overfitting occurs when variance is too high? Yeah, that's exactly right. Because so think about let's see, in this example, the variance of the data as you start to overfit your model will start to increase because you are tightening your model fit to a set of data too closely, and that new data in there increases the variance, the variance error term in the overall error. So what that's going to look like here is that if we consider this to be our error, so overfitting is usually when you have higher model complexity. So overfit is kind of this way, and underfit is this way. So as your model gets more and more complex, the variance will actually increase something like this. And as the model fits the data better and better, your bias will actually decrease like this. And the total error looks something like this. And so the trade-off that you're making is between the bias and variance, and you want to hit this kind of sweet spot right here at the minimum of the total error. And so what you ought to find in your k-fold validation, in your cross-validation, is an effect that looks something like this. So say you had a whole bunch of models that went from less complex to more complex. As you increase the complexity of the model, you're going to see the out-of-sample mean squared error look like this shape, essentially. You will see that the overall error, the average mean squared error of your validation process, will decrease as the complexity of your model increases up to a certain point, and then it's going to start going back up. And actually, we already saw an example of that in the last lecture, right? When we were looking at the stepwise regression, and we're looking at AIC versus BIC across a set of different models, and we could see that the AIC would decrease to a certain point and then start to increase again. And that's at the point where the model complexity, the variance, increasing variance from improving the model complexity, starts to rise again. So this this is a pretty crucial concept for us to think about as we tackle more issues related to like cross-validation and selecting the right model. It's always going to look like this sort of pattern. Okay, I see a question. Can you define variance? Yes. So the formal definition is here. So it's in the green. So this is so f of x, f hat of x is essentially y hat. So it's the variance is equal to y hat minus the expected value of y hat, and then you square that whole thing. Qualitatively, it's kind of like let's see, it's kind of like the spread of the data about the fit. And so if you overfit your data and you introduce new out-of-sample data, the spread of the data about your fit is actually going to start to increase a lot more, as opposed to let me see. So if I were to go back to this example, or I'll just draw a new one. So consider we have kind of a set of points that look like this. And I have a model fit here. So as I introduce new data, the difference between the model fit, aka the line, and the new points, that spread isn't really changing, right? Because it's kind of in the expected value of these points. Compare that to a different fit where, let's say I just do something like this. Now what you can see is that as I introduce new points into the data and compare it to the fit, the variance is actually quite a bit larger because the spread of the data compared to the fit is really different. So that will increase this green term over here, and that's how you capture sort of the error associated with the overfitting. Okay. Do folks have any other questions about that? So this is kind of a topic we'll continually revisit. And so again, this is probably one of the more important concepts to understand here in this class is this idea that the way in which we guide our model selection is oftentimes informed by this whole concept, right? And so, you know, should I choose this model versus this model? It's a question of essentially minimizing these model errors. And we're always going to be trying to essentially evaluate the models on the basis of the bias-variance trade-off. And you can make the models more complex, you can make the models less complex, and the ideal that we want is that point at the bottom of that parabolic curve. Okay, so there's another question. So why does underfitting lead to higher bias? Okay. So this is okay. So here in the red, that's the bias term, and the f of x refers to our the true values of y. Essentially, as your model is like more and more simple, essentially what that means is your f of x here is less able to describe is less able to describe the fit of the points. So the whole idea is basically like you are using a super simple model, and as the model complexity increases, then the fit of of your model to the real data is going to improve, right? And so we've already shown various examples of that in including more variables, or including the right set of variables. And so generally, we just find that the more complex the model is, the closer you're able to get with the actual data. And that's why this term sort of in general happens. So in practice, you'll find that sometimes this doesn't look quite as smooth as this, and that you may have some sort of up and downs and in either the bias curve or the variance curve. So it's not always so straightforward. But in general, as you underfit the data, you typically are missing patterns in the data that you would want to capture, and that would otherwise sort of lead to bias in your fit. And so that's kind of the reason why you see the decreasing curve in bias. Okay, so moving on. So last class, we talked about some classic methods of subset selection that have been around for quite a few decades, and that's very commonly used in many fields. One set of sort of more modern methods that arose out of the machine learning field, which I believe was kind of in the early 2000s, although I could be mistaken about that, is a way of doing, it's kind of like doing variable selection, but in conceptually a fairly different way than probably most of you guys are used to. When you're thinking about how do I decide on which variables to include in my model, I think the stepwise regression is kind of easier to grasp on conceptually, because what you're doing is you're like essentially throwing in variables and figuring out which ones are quote unquote the best through a variety of metrics, right? Which we formalized last time. So in terms of modern methods, there are these two concepts that I'll be introducing today, called shrinkage and regularization. So these are sort of analogous. So some people call it shrinkage, some people call it regularization. And so these will be looking at two particular forms called ridge regression, or we'll be starting off today with two types of regularizations: ridge regression and lasso regression. So let's kind of jump back to fundamentals here. When we do a linear regression, what we're doing is we're minimizing the residual sum of squares. Okay, in other words, you want to minimize the error terms, the sum of the square of your difference between your line and your points, right? So that is equal to in of yi minus beta 0 minus the sum of my betas. So this is more generalized. Okay, so your i's are each individual data point. Your j's are each of your variables. So you could have up to, say, like p variables or something. Or actually, I think we've been using k. So you could have something like k variables. Okay, and so this is my true y, and then this is my y hat, right? So it's just y minus y hat, essentially. And so in a regression, you are minimizing the residual sum of squares with respect to beta 0, beta 1, dot, 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 beta n. So this is kind of like the formal optimization. And essentially what this is saying, the betas are our decision variables. I am allowed, I'm given my x's and my y's, and now I can futz around with my betas in sort of a formal mathematical way, such that I reduce my residual sum of squares to the greatest extent possible. So essentially what happens in the optimization is it will identify the betas. It'll sort of iterate through betas until it lands on the one that decreases your errors to the greatest extent possible. And so what we're going to do in a ridge regression is to minimize RSS with an extra term. And so at the very end of this, we're going to throw on plus this guy, sum of j to p, or sorry, j to k of beta j squared. Okay, so I'll write it again. It'll look something like this. Minimize RSS plus lambda jk beta j squared. So the lambda is something known as a tuning parameter, and we'll talk more about that in just a second. And then this whole thing is known as the shrinkage penalty. Okay, so conceptually, what is going on here? So let's first take a look at the tuning parameter. At lambda equals 0, penalty has no effect, right? And in fact, if I change my lambda to 0, I'm just going to get my original equation because my shrinkage penalty is 0. The larger your tuning parameter is, then the greater effect the penalty will have. So let's think about this conceptually, and actually, I think it'll make most sense for me to write this out so we can do a comparison. So yi minus beta 0 minus sum j of beta j xij plus lambda sum j beta j squared. So if you look at these betas, The betas that have a really important effect in this equation are going to try and stay close to its true value, because the more accurate your important betas are, the more it reduces your RSS, right? So if the slope is close to the true slope, then it's really truly reducing the error. So betas that have an important effect will stay close to true value. And that is, again, because it's going to be decreasing your RSS. Now imagine you've had this model where you have, say, 15 variables, and some of them are important and some of them aren't important, and you just throw them all into the regression. The betas are going to be whatever minimizes your RSS in the original version. But in this ridge regression, the betas that are not important will shrink. So you can see that if your beta values are larger, then that's going against your minimization, because you want to make the whole term as small as possible. So for all the junk betas, essentially those are going to get, in theory, shrunk down to 0 or some value close to 0, because they're not really reducing your RSS, but they are just adding more into your penalty term. Whereas the variables that are important, it's, say, in that 15 set of random variables that I put in there, those will be improving your RSS value. It's going to be decreasing the errors, and so it's kind of worth it to have them close to its true term, despite the fact that you have some penalty happening by having your betas sort of be larger.
Alan, I have a follow-up question on the conceptual understanding. So when you say that the betas that have an important effect will stay close to the true value, but like in the way this is being formulated, you calculate all the betas anyways. So how do you actually distinguish which ones have an important effect and which ones will shrink?
By their contribution to the error term, right? So think of it this way. If I have x1, x2, x3, and I put in x1, that's going to, I'm going to have some set of residuals, right, associated with with my model, with beta 1, x1. And then if I have, and I can add up all those residuals and get my RSS, and it'll just be this one number. Now, let's say I throw in x2, and now I have a different set of residuals, right? Because it's fit through 2 variables, and I can take the difference between I can sum up and square all my residuals, and I have a different number. And so the concept here is that you actually enforce a penalty term on my betas, so that suppose I add in my x2, and that beta, or not, sorry, not that beta, the RSS associated with adding in that second variable is going to decrease. It's always going to decrease my my RSS,
Right.
but now it's going to increase a penalty term. And you'll see that, so the thing that often gets confused here is that the betas that you get from a ridge regression are not the betas that you're going to get from a linear regression. They're actually going to modify the betas in such a way that it's going to decrease the ones, it's going to decrease the size of the coefficients for variables that do not affect the residuals as much.
I see. Yeah, so what you said about how the betas from the ridge regression will be different from the betas in the linear regression, that's due to optimizing RSS plus the shrinkage penalty term, right?
Exactly.
That makes sense. Thank you.
So it's a new optimization that's going on here.
Hey, Alan, I had a quick question as well.
Yes.
Yeah. So in the last class, we discussed about stepwise regression, and that again is a method to identify the most optimum variables to be included in our model, right?
Yes. Yeah. That's
And
one way of trying to do that.
okay, and these methods, these so-called modern methods, the ridge regression and lasso, are also doing the same.
Yes, but in a really, really different way.
Okay, so my question is, if we just run a simple regression and we look at the results, so we've got R square and then there is the corrected R square. So whatever I understand is the corrected R square actually has some considerations for the additional variables that are incorporated. So
Yes.
what information does these modern methods give us, which we are not able to get from that corrected R squared value? For example, we look at the corrected R squared value and we know that, okay, the effect of these variables are nullified and we get this R squared. So our fit is good enough.
Okay.
Then
So
why do we have to go into these modern methods then?
yes. So I think, as I've sort of tried to explain in the past, that the R squared is not a good sort of end all be all metric for the quality of your model. And it's really something we should stop doing, to just say, oh, I have a good R squared, and therefore my model is good. Okay. There are lots of other considerations, such as, a handful of the metrics that we've talked about. And in fact, oftentimes what you'll find is that the R squared can be the R squared can lead you to models that are not nearly as good as a lot of models that can be devised through some of these approaches. In addition, it's only a metric. It doesn't give you any techniques in terms of identifying a particular model specification that you want, right? So last time, one of the things that we talked about was, if I say I have 100 x variables, okay, so this leads to 2 to the 100 combinations of specifications.
Yeah.
So you could attempt to run all of those combinations of variables, and that would take you probably the rest of your life to do, if not longer. Or you could run a stepwise regression, or you could do a ridge regression and throw all of these variables into that algorithm and be able to devise the correct specification, right? And so the adjusted R squared is only a tool within actually a lot of these algorithms that help you do that identification. So we're kind of talking about separate things here.
Okay. Okay.
Yeah.
Gotcha.
Does that make sense?
Yeah. Really. Thank you.
Mm-hmm. Okay, I see another question. Will the shrinkage penalty increase with the not important betas? Is that what shrinks their effect on the min RSS? So, okay, so yeah, what's happening here is so it's making an adjustment where for the not important betas, if the betas were large, then the shrinkage penalty would be large. But essentially, it's going to do this trade-off where it's going to start to decrease the betas on the, I guess, the not important ones, as we're calling them. And so as it decreases the value of my beta for a not important variable, it will both decrease the RSS and decrease the penalty term. Or sorry, it will increase the RSS because you are making the betas smaller, but it will decrease my shrinkage penalty term. And so I'm going to try and find the sweet spot so that's such that as I decrease the size of my betas, particularly for the non-important betas, the amount of increase in my residual sum of squares is more than offset by the decrease in the shrinkage penalty. And I'm gonna hold off on explaining this more because I think visually we're going to be able to see essentially what this looks like once I do an implementation in R. And hopefully that will get your minds a little bit more latched on to a practical example. So I'm really quickly going to go through the Lasso regression. And the Lasso regression, so it's pretty easy to cover this now that we've talked about ridge regression. It's exactly the same thing, except that the penalty term is a little bit different. It is like this. So instead of squaring the beta j, it's taking the absolute value. So absolute value instead of squaring. So in more practical terms, so in a ridge regression, what you tend to see is beta shrinks to 0, but don't actually get set to 0. Whereas in a lasso regression, when my tuning parameter is large, betas get forced to 0. Okay. There's one last thing to talk about before I get to the examples, and I kind of want to pose this as a question. Can anyone think of how we would go about getting the value, or how would we go about deciding the value for our tuning parameter? Should it be close to 0? Should it be really big? Like, how would we decide the tuning? So I'll give you a hint. So the tuning parameter, one way to think about it is that as you increase the size of the tuning parameter, you're essentially decreasing the model complexity because you are essentially saying that I want I want to penalize closer fits. And so, well, I guess I'll just say it. This again goes back to our original concept of the bias-variance trade-off. The way in which you often decide the tuning parameter is through cross-validation, and you test a bunch of values of the tuning parameter. And we'll cover that in code. So let's take a quick break. I am running a little bit behind, so let's just do, say, like 3 minutes today. So we'll reconvene at 11:17.
Can I ask you a question about the homework?
Yeah.
I am, for the third problem, the Doris one, I'm having difficulty setting for ggplot the odometer readings to like red.
Yes.
And it's because it says it's continuous data set, not discrete. I don't know like exactly how to work around that.
Yeah, so my suggestion would be something like this. So I'm kind of going to write some pseudocode for you. Oops. So the way that I would think about doing it is to separate it into 2 sets of points. And then you have your XY, and you have your XY here. And you can just type out
Okay, so separate.
like that. Yeah.
Okay.
The alternative way to do this would be like this. Let's see. Color equals odometer. I don't know if this is what you were trying. And the color is equal to the category of whether or not the odometer is working or not.
Yeah, that was the first approach that I took.
Yeah, so that should work.
It works the gradient for some, but that's because I think.
Yeah, so the only thing is it depends on how, I don't remember exactly how I asked for it to be coded. Like if it's, no, I guess even if it's 0 and 1, it should work. Yeah, I think either of these should work pretty much in all cases. Yeah.
Okay, that's helpful.
Yep.
Oh, great. Something too. The other way I did it was to change the odometer to a factor categorical. Okay.
Okay. I'll just comment this. Question on homework 3, plotting colors. So before I get to the demonstrating the ridge and lasso regression, I want to kind of really quickly, cover the concept of the bias-variance trade-off in a more practical example, so that hopefully we can get a visual and practical representation of the concept that I was talking about, and I will be implementing this in R. So I'm going to go through this kind of quickly. Again, the code will be made available online, but I will talk through this. So this part, everyone should be super familiar with. We are just making a set of random points from X and Y. And now I'm actually going to, what I'm going to do is add exponential explanatory variables. So I'm going to add x squared and x cubed. And sort of as I mentioned, as you increase the number of variables in trying to describe your data, you're always going to get a closer fit with the actual. And so what I'm going to do is, even though I know the true form of my model is just based off of x, I'm going to start adding in extra explanatory variables, x squared and x cubed, and we can see sort of what this looks like. Okay, oh wait, I didn't run that, I think. There we go. So I'm going to do summary. Okay, so again, to go over this again, I have created a linear fit fitting to x, and then fitting to x, x squared, and then fitting to x, x squared, and x cubed. And let's take a look at the summaries for each of these guys. So here, and so, okay, we'll mainly pay attention to my r squared here, 0.29, and then summary model 2, 0.2957, and then look at model 3, 3606. And so essentially the fit is getting better and better, or I'm describing more of the variation as I include more exponential explanatory variables. Essentially what's happening is the line is going to start to wiggle and get closer to the points as you add exponentiated terms. So now let's take that to the extreme. I'm going to copy and paste a whole bunch of code in here, and then we're just going to walk through what is going on. But I guess the most important thing is kind of the concept. Okay, so where were we? Okay, we were right here. So I'm going to do essentially the same thing as I did manually over here with x squared to x cubed, but I'm actually going to go all the way from x to the first power to x to the 50th power. And that's all that this code is doing. And I'm going to create an example data frame. If I go ahead and click here, we should be able to see. So I have x1, x2, which is x1 squared, x3, which is x1 cubed to the 4th power, all the way up to, you know, the x to the 50th. Okay. And now what I'm going to do is I'm going to create a data frame in the predict function for x1 to x50. And that's going to give me the fit. Okay. Now, one of the convenient things so this is not something that you would normally be able to do with a data set, but we have the true function, so we can create synthetic data. This is the reason why we do cross-validation and out of sample is because we don't have access to like synthetic data usually. But in this case, because I know this is my true function, I could just make new data artificially. And so I just create a test set. And so the test set refers to data that my models aren't training on. And then this is all sort of just like accounting stuff to hold it into a specific data frame. And now this is going to do our cross-validation, where we're going to essentially run our model of x1 and then x1 and x squared and x1 x squared x cubed all the way up to x to the 50th. So now we have 50 different models, and they are going to predict against the test set. And then we're going to calculate the mean squared error of the out of sample. And so this is all the code that does that. So I think if we take a look at the graph, this will become a little bit more clear. Okay. Give it 1 second to render here. Okay, so I've got 50 models, and it's the same set of data points, and then the red line is my model fit. Okay, and the model fit is derived from regressing, y on x1, and then for 2, y on x1 and x squared, and then 3 on y on x1 or x squared and x cubed, and so on and so forth. So what you'll notice is that as you add more exponentiated terms, your line essentially gets a little bit more, I guess, like wiggle. And actually, one of the artifacts of the exponential terms, and we'll actually talk more about this whole concept of adding exponential variables later on as we approach non-parametric techniques. You see that the line starts getting curvier and curvier, and essentially the line is, or especially at the edges, is where it gets really, really curvy. But all of that is sort of calibrated in such a way, so the betas are calibrated in such a way that you're going to get closer and closer to the points. Let's see. I may have to even make this a little bit bigger. So I'm running the same thing again, but now it's got a couple numbers associated with it. So give it 1 second. Okay. Let's see. Let me make sure I'm reading this right. So x is 0. So that's the training and the testing. Yes. Okay. So let's look at the number in the top left side. That is the in-sample mean squared error. So that is the error associated with the points that we have calibrated on. So this would be kind of analogous to looking at like the R squared. And what you'll find is that the error will continue to decrease as I add more and more terms. So I start at 117, it goes to 116, and so on and so forth. Okay. And that's because the calibration of the model gets closer and closer to the actual data points, which means my residuals are getting closer and closer to my fit, and my error goes down. And that is exactly sort of what I'm expecting, right? But now this plays to this concept of we may actually be worried about overfitting the model. And so if I were to calibrate the error not on the points that I've calibrated my model on, but I look at the error associated with the points outside of my sample, you'll actually see that it increases continuously. I mean, you may have some decrease, so like actually 8 to 9 actually goes from 245 to 244. So you do have some fluctuations, but in general, you are actually continuing to overfit the model. And so this is speaking again to this bias-variance trade-off, where as we overfit the model, you're increasing the variance error component term, and that's leading to actually a larger out-of-sample mean squared error as I add more terms to it, even though it's fitting the points better. And actually, in this particular example, I should probably change the function so that we can see the overall error sort of going down and up. In this case, it starts at the smallest error because we know that the true function is only a function of x and not x squared and all these terms. But if I did have it as like x to the fourth, what you'll find is that that the x to the fourth would have the smallest error term, but because it's the true function is just x, any increase in model complexity is actually increasing the overall total error. Okay, so again, let's take a step back and think about what this means. When I have this ability to measure the out-of-sample error, that's how I get to my true function, right? So it has landed precisely on the model that describes our true model. And it's a really sort of powerful way of leveraging predictive ability on out-of-sample data sets to get at the best model. Okay, so I think this should clear the plot, right? Yes, okay, good. Okay. So hopefully that's clear. And how do I bring this back down? There's no, there we go. Yes, so in chat, this shows how the k-fold method relates with the trade-off. Exactly. This particular example wasn't using the k-fold method because I just generated synthetic points. The k-fold is the method of generating out-of-sample data that you can use as a testing set. But in general, that's exactly right. By doing out-of-sample testing, you are able to replicate that total error curve that identifies the trade-off. And the k-fold method is a great way of doing that. Okay. So let us go on and talk about the ridge and lasso regressions and apply actually this whole k-fold idea into identifying the lambda. So, oops, I'm going to copy and paste a little bit of stuff here. So we're going to take a look at the same data set that I got from before, from ISLR. Apparently I don't have GLMnet installed. Well, let's take a look. Okay. One moment. So last time we took a look at a data set called credit. And let's quickly take a look at this again, just to refresh everyone's memory about this. So credit gives a whole bunch of variables like income, credit limit, credit rating, number of credit cards, and some demographic information, as well as the average monthly balance of debt on credit cards. And we wanted to look at a linear regression of all of those variables so we can see what that looks like. So this is our linear regression. Oh, yeah, I should just note really quickly that I have added this. So we talked about what the dot means last time. That means include all the variables. If you do +0, that just means you don't want an intercept. And the reason why I'm doing that is so that I can compare apples to apples with my ridge regression, which I'm going to specify as not having an intercept. I don't know exactly why they do that. It's just the example that I based this on. They toss out the intercept, so I'm doing the same thing. Okay, so let's take a look at a ridge regression. And the way that you run it is with a function called glmnet. And it takes in your variables in this way. You have to create a model matrix. And let me show what that looks like. Did I actually run this yet? I did not. So a model matrix is a certain type of matrix that contains the data in a model form. So it looks something like this. So it basically says these are the variables to regress on against balance. And that's what you need to feed into glmnet. So x equals x, y equals y, which is a vector of my explanatory variable, or my response variable, not my explanatory variable. Alpha equals 0, and lambda equals 0. One moment. So the alpha is related to the penalty term actually for a Ridge regression, you set the alpha equal to 0. For a lasso regression, you set the alpha equal to 1. And I'll show that later. Lambda is our tuning parameter. So remember what I said about our lambda. If we set it equal to 0, it should be exactly the same as our linear regression. So if I type summary of my ridge regression with a lambda of 0, oh man, okay, hang on. It's you don't use summary, you have to use I think it's ridge beta. Yeah. Okay. Let me see if there's a good way of getting these both on the screen. Okay, well, at equals 0, you know, income of -7.8, credit limit of 0.21, so on and so forth. And it should be really, really close to my actual linear regression. There are some, so in theory, it should be exactly the same. But in reality, it's going to be slightly different. And the reason for that is because a linear model is a closed, it's an analytical solution. So if you remember, if you've taken in the stats class for regression, you've got that, what is it, the xtx inverse times ytx to calculate your betas, something like that. I can never remember it off the top of my head. And that gives you the exact solution for your betas. Whereas in the ridge regression, it's actually running a numeric solver for an optimization. So it's going to get close to some boundary and then it's going to say stop. And so that's why you're not going to get exactly the same, but essentially it's going to be pretty close to your linear regression if you set your lambda equal to 0. Okay, so we want to pick the optimal lambda, and the way we do that is through our cross-validation k-fold. So what we're going to do is we're essentially going to select a random, sorry, not a random, but you're going to select a value for lambda. You're going to perform cross-validation. You're going to obtain the average test mean squared error, and you're going to repeat steps 1, 2, 3 across a range of different lambdas. So that essentially what you're doing is you're saying, okay, if I change the tuning parameter to a specific value, how well is my regression now going to, how well is it going to do out of sample predicting? And then I'll change the lambda to a different value and say, okay, now how is my regression going to predict out of sample? And you're going to do this until you find a lambda which yields the lowest average test mean squared error. Okay, so that is what this code is doing. And I'm not, again, I'm going through this pretty quickly. And so this is definitely something worth reviewing and looking over sort of on your own time if you don't understand it. One of the things that you'll see is that this function that I've created manually. So first of all, I will say that there are built-in functions that are just going to do this for you, and that's totally fine to use. I kind of just want to explain manually the concept here. So hopefully you understand what's going on behind the scenes. You'll see that this particular function is pretty similar in structure to the function that I had made in the previous class when we did a k-fold validation for cross-validation for stepwise regression. Here we're going to do the same thing, but we're applying it to lambda. So the data input, the number of folds that you want, and then lambda and alpha. So we are picking numbers out of a hat and creating an index, and then we are going to actually, I feel like there should be an assignment of the index here. Oh no, actually it's in the rows. So yeah, it's doing the same thing. Basically, I'm going through the number of folds, and then I'm creating a training set and a testing set. Okay, I'm running my ridge regression based on my value of lambda. I'm going to predict it and then look at the out of sample mean squared errors. And I'm going to do that a whole bunch of times across a range of lambdas. And the lambdas that I'm going to look through are here. And I'm going to actually go by order of magnitude. I'm going to look at like 0.01, 0.1, or 0.001, 0.01, 0.1, and 1, something like that. And we'll look across all of these guys, and then let's plot it and see what this looks like. Oops. It's actually saving a figure. What you can see here is the overall error of my lambda. So as I change the value of my tuning parameter, as it gets larger, this is actually going to be this is actually going to be in slight reverse, because as the lambda gets larger, your model complexity is actually decreasing, and as it gets smaller, your model complexity is increasing. And so this is kind of the mirror image of the bias variance trade-off. So your variance is increasing to the left, and your bias is increasing to the right. And we can see as it gets smaller and smaller, actually it's actually getting better and better. And so let me go ahead and show a different plot. So this is what happens to the variables, to the betas, as you change your tuning parameter. At a lambda value of 0, each of these points related to each of the variables are going to be equal to the coefficient value in your linear regression. So if I just ran a regular linear regression, not a ridge regression, on a model where I include all of these variables, then the student yes would have a coefficient value of about 400 something, and actually we can see that, right? So let me just, oops, it would be in here. So let's go ahead and take a look at this. So student yes at 425 So that's this value. The next largest is cards. So that's the green value up here. And you also have ethnicity Asian at 16, which is this value. And what happens is as your tuning parameter increases, as your tuning parameter increases, it's going to decrease the size of your betas. There's one that happens to be at a like different order of magnitudes, so it's a little bit harder to see, but essentially as the lambdas increase, the sort of less important ones are going to start to approach 0. And you can see that, you can see the difference, right, between this purple line and this green line. The purple line starts to decrease first before the green line, which would kind of indicate to you that that the cards is more important than ethnicity Asian for the purposes of predicting out of sample. Okay, and each lambda that I've run is going to lead to, some sort of mean squared error, out of sample mean squared error. And I can sort of nail down the best lambda. And then I could then run the model again and sort of use that as the best sort of model. And so I've gone ahead and done that, and it turns out when I do like a close examination of my lambdas, that the best one is at about lambda equals 5. And so let's take a look at that. So let's do ridge $beta. And now we can see and compare this. Okay, I don't know why I have this here. Get rid of that. So now we can compare against our linear model. And you can see that it's actually fairly similar, but that some of the coefficients have been altered in size, and so actually this out of sample prediction is actually going to do a better job than in the linear model, because it's run the out of sample lambda at 0, and it's actually saying that lambda at 5 is better. So this can be a nice sort of way of being able to, without taking variables in and out of your model, sort of determining their effect in such a way that you get the best predictive model possible. Okay, I see a question. So to see which variables are more important is seeing when the curve starts to decline. Well, that's kind of like a qualitative way of doing it. Basically, at the end of the day, you probably want to end up doing something like this, where you test a bunch of different values of lambda and then identify the best model, and then you just sort of use those values. How about the magnitude of changes associated with each variable? Yeah, so that can be important as well, for sure. But again, you're not really kind of looking at this graph as a way of deciding the importance of the variables. It's more sort of a qualitative view. You can do some comparative look at the effects of different variables and how they change as your lambda changes. Let me see. So I think this is a closer look at the lambdas. And you can see there are some fluctuations up and down. In this case, in this particular example, it's a little difficult to see the bias-variance trade-off. But probably as I go down and approach smaller values, you'll start to see maybe a small increase. Okay, let's take a look at no, okay, sorry. This is different. This is yeah, this is the same thing, except I'm looking at the lasso regression, not the ridge regression. And we can see, probably it's more easy to see the difference in the way the variables approach zero. So I mentioned in the notes right before we went to RStudio is that with a ridge regression, they tend to approach zero asymptotically, whereas in a lasso regression, it kind of forces the values to, it forces the coefficient values to zero. And you can see that happening here. And in fact, if I were to run my lasso model with the best lambda, so the best lambda in the lasso in this case is 0.211886. You can see, let's see, lasso beta, there should be, well, actually, in this case, you still get similar results, but if you increase the lambda, let's just say lambda equals 3. Is that the log lambda that I have going on? Yeah, it is. That's why. So not 3. Let's go with 10,000. Okay, in this case, it's way too big. All my betas have gone to 0, which is not something that you'll see in a ridge regression. It will sort of approach 0. So that's kind of the main difference between the lasso and ridge. There are some more nuanced reasons for why people choose one versus the other, but a lot of it actually boils down to kind of personal preference for the behavior of your coefficients. Okay. Again, I think I went through this pretty quickly, so definitely review some of this code, try and understand what's going on here. Really essentially what we're looking at is the application of ridge and lasso regression in such a way that we can determine what the right values of lambda is. And the way we do that is through cross-validation and doing this out-of-sample testing. And you identify the best lambda by looking at the lambda which provides you the smallest mean squared error. Let's take a look. So now I'm just going to quickly show ridge and lasso regression with built-in cross-validation. So as I was saying, these guys, the creators of the package that does the ridge regressions, they don't expect everyone to be able to write out their own function to do the cross-validation. And in fact, you have a built-in version of this already. And so the way that you do that. Hang on, let me get rid of these. Okay, so the built-in cross-validation is with this function where you have cv.glmnet, and you can identify it by running this. If I plot ridge.best, it is going to give, similar to what I was doing, showing the mean squared error, but it has an automated way of figuring out the bounds for the lambda, and it's identified the mean squared error is lowest right here in this area. And it can also plot the coefficients. So this is the same graph that I was showing before as well. And so, yeah, so this goes through the whole out of sample cross validation procedure that I did by hand, and all you have to do is cv dot. So significantly easier. But you can see, but I've left the code as a reference for you so that you can see what's going on behind the scenes. GLMnet, where you have, where you specify the lambda, here I'm choosing from my cross-validation the lambda.min, which gives you the lambda, which minimizes your error terms. So this is what we were trying to find manually again, and here you can just enter it in like this. And we should be able to see the betas, which are determined here. And so in this case, we can, if you compare this against the linear model, you will see a sort of marked difference in the size of the coefficients. And that is because the coefficients are being modified by the additional penalty term. And we can do the same thing for our Lasso regression, just so that we can see before class ends what this looks like. Here's your mean squared errors across a range of your tuning parameter. And we can see how the coefficients change as a function of your lambda as well. We'll do the same thing and look at the lasso. And actually, you'll find that the lasso regression and the ridge regression give slightly different answers, again, because of the way that it modifies the betas, happens differently. And in fact, you could go and look at the average out of sample mean squared error for your ridge regression versus your lasso regression to determine sometimes one approach can be better than the other. Okay. So I don't want to go too much over our time for the day, but this was a pretty rapid introduction to some more machine learning based techniques of doing model selection through, again, what's called regularization or shrinkage, of which we've learned two approaches. One is the ridge, one is the lasso. These are in concept similar essentially to what the stepwise regression is doing. You have a bunch of variables and you want to figure out which ones to include in such a way that you prevent overfitting. And the stepwise regression prunes the variables themselves. So you select which subset of variables will allow for you to minimize overfitting, whereas in the case that we did today, with the ridge and lasso regressions, you are pruning the effect of the betas in such a way as to avoid overfitting. Yeah, and so really kind of different ways of thinking about how to do your model selection. this is maybe unorthodox to a lot of you in terms of traditional thinking about selection for just the variables, but in this case, you can actually select based off of the size of the coefficients. And one of the nice things about this, which really kind of bodes to the way machine learning algorithms tend to approach data analysis, is I can just toss in all the variables and then run the ridge regression, and all of the ones that don't really matter, those betas will shrink to zero pretty quickly. And so it's a pretty kind of hands-on or hands-off approach in being able to think about which variables go into the model. Okay, so, oh, I see a quick question. When lambda equals 5, RSS is minimized. No, I think that I might have just, in this particular example, I'm not sure if that's the smallest value. Actually, I could just take a look really quick. Ridge dot best dollar lambda dot min. No, I think I just chose a random lambda so that we could do a comparison. So the actual min, I think, is about 39.7. Okay, so we'll end here for today. Again, I'll stick around for a couple minutes in case there's any questions.